Alright, so in this video, we're going to discuss one of the greatest methods for basically a shortcut for taking derivatives, the power rule. Right, so at this point, you should have been used to, when they're like, find a derivative, you've been using the definition of the derivative so far, most likely. I'm not sure what order certain classes go in, but now we're going to start looking at shortcuts for calculating derivatives, and the first one typically taught is the power rule, okay? So what the power rule says is, say you have some function in this form, ax to the n power, where x is a variable, a is a coefficient, and n is some numbered exponent, right? So it could be anything like 6x to the 10th, 4x to the 18th, 7x to the 42nd, just 1x or x to the second. Whatever it is, if it's in that form, we have a really quick, short method for calculating the derivative of that, okay? And that is just to multiply, so this a and n together, right? You're essentially bringing this n down up front and multiplying that, and then you're decreasing the exponent by 1. Simple as that. And it's much, much quicker than doing the definition of the derivative. This was actually derived from that equation. Like, the definition of the derivative is why we are able to have all these shortcut rules, but now that we have them, they're just a lot nicer to use. Now let's go into some examples, because I think that's the best way to kind of show the power rule. So I wrote down a couple of simple examples here, and we'll get into more complicated stuff in a bit. But first, we're going to start off with 5x to the 8th. Okay, f of x equals 5x to the 8th. How do we take the derivative of that? So that's in our form where we have x with some coefficient and some exponent. What do? Well, first we're going to multiply our exponent and our coefficient together, our a and our n term. So 8 times 5 gets us 40, and then that's x to the n minus 1. So our original n was 8, so n minus 1 is 7. Simple as that, right? Much less steps than using the definition. So let's look at the next one. All right, we have 3x to, and it's not written, but 3x to the first. Okay? So if I write it there, just temporarily, right? What's the rule? Well, I multiply my exponent and my coefficient together, so 3 times 1 is 3. And x to the first is now going to be x to the 0, right? N was 1, so n minus 1 is 0. Now, anything to the 0 power is just equal to 1. So 3 times x to the 0 is the same thing as 3 times 1, which is just 3. Now, that brings us to kind of one of our first, even shorter shortcut methods for power rule. Anytime you have a x, right, where your exponent here is always 1, then the derivative of that is just a. It's just the constant up front. So the derivative of 10x is just 10. The derivative of 105x is just 105. That becomes very useful later on. Okay? So let's take a look at the next one. The derivative of 7 times, well, you don't see it here, but you could also write it as 7 times x to the 0 power, right? But since, like we saw here, we don't really write to the 0 power, we normally just write 7. So let's take the derivative of this and see what happens, okay? So first, we multiply our exponent with our coefficient. So 0 times 7 is just 0, multiplied by x, and then we decrease our exponent by 1. So 0 minus 1 is negative 1. So we have 0 times x to the negative first. Now, 0 times anything is just 0. So the derivative of 7 will just be 0. That brings us to our second shorter shortcut method using the power rule. anytime you have a constant, right, like a, the derivative of a constant is always 0, right? So let's say g of x is equal to a. Derivative of g of x is just 0. So the derivative of 100, 0. The derivative of 8,000 is 0. Derivative of 4 million is also just 0. Okay? So that comes in handy a bunch later. So let's take a look at our last shortcut example before we go into some of the more complicated ones and some of the ones you will more commonly see. X to the negative third power. So again, we're just doing the power rule again. There's technically a 1 up here, so we multiply our existing coefficient with our current exponent. So 1 times negative 3 is negative 3. And then x raised to the negative third, so our current exponent is negative 3. Negative 3 minus 1 is negative 4. So this becomes negative 3 x to the negative fourth. All right, simple as that. Okay, now let's look at some more complicated examples. All right, so these next two examples are pretty common forms to see stuff in, to be asked to take the derivative of something like this polynomial. What really helps us out is the specific rule with derivatives. When you have a bunch of terms separated by addition or by subtraction signs, you can take the derivative of each term individually. Now, this isn't true for when you're multiplying or dividing things. There's a separate product and quotient rule for that, and I have videos on that already. But this is very useful when taking the derivative of polynomials, right? When I'm adding and subtracting things, I can individually take the derivative of each term. All right? So this first one, we have 5x to the third plus 9x to the second plus 12x plus 81, right? Definition of the derivative would still work, but that would take forever. So let's use the power rule, right? First, let's take the derivative of this thing, 5x to the third, our first term. So that's in the proper form we want of that ax to the n power. And we just, first step is to multiply our existing exponent with the current coefficient. So 3 times 5 is 15. And that's now x raised to the old exponent minus 1. So 3 minus 1 is 2. Plus our next term, 9x to the second. The derivative of 9x to the second, we can use the power rule. So we bring our existing exponent down and multiply it with the current coefficient. So 2 times 9 gets us 18. And then it becomes x to the, what is 2 minus 1? That's just 1. And we don't need to write that. So our derivative of 9x to the second is just 18x. Okay? Plus. Now, what's the derivative of 12x? That one is pretty easy. We've determined before that anytime you take the derivative of something x, right, any ax, it's just going to be a. So the derivative of 12x should just be 12. And then plus derivative of 81. And like we did before, the derivative of any constant number, like without a variable, should just be 0. So this would just be a plus 0, which we don't need to write. Okay? So our final answer would be 15x squared plus 18x plus 12. Now let's look at another example. It looks longer, looks a bit more difficult, but it's much easier than it seems. You're doing the same steps over, right? You have a bunch of stuff separated by addition and subtraction signs. So you can individually take the derivative of each term. So let's go term by term. Our first thing is positive 2x to the sixth. What's the power rule? Well, we take the exponent and multiply it with the coefficient, right? We're bringing this down. And that's becoming 12x to the 5th minus our next thing, which is x to the 5th, and we take the 5, multiply it with the existing -1 to get a -5, x raised to the 5 minus 1, which is 4, plus, so like I said, like I've been saying, right, we take our existing exponent, multiply it down with this 4. 4 times 4 is 16. That's our new coefficient. Times x raised to the original exponent minus 1. 4 minus 1 is 3. Plus 10x to the 3rd. Bring our exponent down. 3 times 10 is 30. X raised to the original exponent minus 1. So 3 minus 1 is 2. 30x to the 2nd. Plus 6x to the 2nd. Bring the 2 down. Combine it with the 6. Multiply it to become 12. Our new exponent is 2 minus 1. Becomes 12x to the 1st. And from the rule I stated earlier, negative 37x, the derivative of that should just be negative 37. And the derivative of our constant 12 is just 0. So this would be our final answer. And hopefully from here you can see the usefulness of the power rule, right? It takes something that looks super complicated, that based on the method you already had would have taken a very long time to do. And I did that in less than a minute. Okay, now let's look at a couple of different examples. The next thing I want to talk about is what to do when your exponents are fractions, or you're dealing with square roots, or something not in a form that you're used to. Okay, so like we discussed before, what you need is that ax to some exponent term, that ax to the n form, in order to use the power rule. So if something isn't automatically in the ax to the n form, you might be able to get it that way. And radicals are an example of something you can convert. So you should already be familiar with this kind of conversion, where say you have some x in a radical. Say x is raised to some number m, and it's in some n root. You can convert that to becoming a fractional exponent, right? This should be equal to x raised to the m over n power. Okay, so similarly, we can do the same thing here. There's technically a 2 here, it's a square root, so this can become x to the 3 over 2 power. Now it's in that form that we want it to. There's a 1 out front times x raised to some power that's a number, right? So now we can use the power rule. So how do we take the derivative of this? So this is f of x. So what is f prime x? We actually use the same power rule from before, right? We're going to take this exponent that currently exists, multiply it to the front. So 3 over 2 times 1 becomes 3 over 2, and that's multiplied by x raised to the 3 over 2 minus 1 power, right? X to the 3 over 2 minus 1 power. Now, subtracting with fractions is something, for some reason, a lot of people have trouble with it, right? It's something you maybe went through in 7th grade and you're kind of okay with it, but it comes up a surprising amount in calculus, just being able to subtract with fractions. So make sure you're really good with that, because I've seen a lot of people just kind of get confused with this, that part of it. So 3 over 2 minus 1 is the same thing as 3 over 2 minus 2 over 2. So this can equal now 3 over 2, oops, sorry, that should be 3 over 2 times x to the 1 over 3. All right. Now, if you're required to convert that back, you can bring this 3 and make it a root. Oh, sorry, this should be 1 over 2. My bad. 3 over 2 minus 2 over 2 is 1 over 2. So you can convert this back to being a root, and this will become now 3 times square root of x all over 2. Okay? So although it looks more complicated, it is the exact same rule that you've been using this whole time. So now let's look at another example, right? A little more complicated. We have stuff separated by an addition sign. So we go term by term. First, we want to convert all the terms into the form we want, like some a term times x raised to some exponent. So let's go. The square root x, this is a 2 here and a 1 here. So this becomes x to the 1/2. And now we add it to the 9 times third root x to the 7th. That's going to become 9 times x raised to the 7 becomes the numerator, and the 3 becomes the denominator. Okay, now we can take the derivative of this very easily. So f prime x. We take the existing exponent, multiply it to the front, right? We bring this down. So it's going to be 1/2 times 1, which is 1/2, x raised to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. And then we add it to the 9 times 7 over 3. Now, we follow the same steps. 7 over 3 comes down in front and multiplies with the 9. And that becomes 63 over 3. Times x, and then 7 over 3 minus 1. 7 over 3 minus 1 is the same thing as 7 over 3 minus 3 over 3, which becomes 4 over 3. And that's our final derivative. So those examples may seem a little more complicated, but typically what you want to do is anytime you see a square root, convert it to a fractional exponent. And then it might be in a form you're more easily able to manipulate. Okay? Now let's look at negative exponents and how to deal with those, along with fractions and variables in the denominator of a fraction. So hopefully these next examples seem somewhat reminiscent of the last examples. So let's look at this first one. 3 over x to the 4th. Now, similar to what we just did with the square roots, this is not in the form we want, right? We want some number times x to an exponent. How do we get this x term into our numerator where we need it to be? Well, we negate the current exponent. So this is equivalent to 3 times x to the negative 4th, right? A technique you should be familiar with doing at this point. Now this is in a form where we can take the derivative. So let's do that. F prime of x is equal to, we take our existing exponent, multiply it to our current coefficient, right? We bring this negative 4 down. Negative 4 times 3 should be negative 12. And we decrease our current exponent by 1. Negative 4 minus 1 is negative 5. So this just becomes 12x to the negative 5th. And that's pretty much it. For the most part, you're probably going to be allowed to leave it like this. If you're required to have positive exponents, then you would need to convert this to becoming negative 12, bringing your x to the negative 5th down to becoming x to the positive 5th. All right? And it's simple as that. Really, it's just a couple of steps. It's just remembering that rule and knowing how to convert. In our next example, something similar. Our x terms in our denominator, we need it in the numerator. So how do we bring it to our numerator? We negate the current exponent. So we have 2 over 3, and we bring our x to the top, and it becomes x to the negative second. And then we can make our 2 over 3 kind of a coefficient like this. 2 over 3 times x to the negative second. Simple, right? So now that it's in the form we want, a number times x to an exponent, f of x, the derivative of that will be, we bring our current exponent down and multiply it with the coefficient. So 2 over 3 times negative 2 will be negative 4 over 3. And then x raised to the negative 2, we need to subtract the exponent by 1. That's going to become x to the negative third. And then if you wanted to convert that, that would end up becoming negative 4 over 3x to the positive third. And that's pretty much it, right? It really isn't more complicated than that. Now let's look at an example where, we have some stuff separated by an addition and subtraction sign. Okay, so let's see here. We have 4 over 7x to the third, and then that's added to 2 over 2x to the negative fourth. So we can do it one by one to take the derivative, right? The same rule still applies. When things are separated by addition signs, we can take the derivative individually. All right, so first thing, let's convert all of them to the form we want. So the 4 over 7x to the third can become 4 over 7 x to the negative 3. And then plus, this doesn't make sense to have. I'm going to just change this to 2 over 3 rather than 2 over 2. I didn't realize I had written that. It's kind of weird. So it's going to become 2 over 3 x to the positive fourth, right? Because negative of negative 4 would become positive 4. Now we can do a derivative. So power rule says for the first thing, first term, we bring this negative 3, multiply it out with the coefficient, we bring it down. And that's going to become negative 3 times 4 over 7 should become negative 12 over 7. And then x raised to the negative 3 minus 1, which is negative 4. All right, and that's plus, we bring this 4 down to become 8 over 3 up front, x raised to the third power, 4 minus 1. And really, it's as simple as that. This is a really quick and easy method for calculating the derivative of these kind of functions. Okay, now let's look at just one last thing where I kind of combine the last two example types we went over of radicals and fractions. All right, so this is the last thing we're going to look at. Now, I'm not going to do a full, do a couple of examples of different terms. I really just want to emphasize that, you can convert something that looks even as kind of complicated as this into something you can use power rule with. I feel like at this point, you should have a good grasp of power rule after those examples. I just want to go over converting something like this. Okay, so say we have some function. F of x is equal to negative 2 over the fifth root of x squared. How do we get that into our power rule form, right? A, some number, times x raised to some exponent. Well, first, let's convert this radical. That's the first thing I think you want to do, is get rid of radicals, have only exponents. And that's going to be negative 2 over, or the negative can be in the front of the fraction if you want, And then this is going to convert to becoming x to the 2 over 5. All right? So now we got rid of our radical. How do we get rid of our fraction? Well, same rule as before. We bring the x up to the numerator and negate our exponent. That's going to now be negative 2, x raised to the negative 2 over 5. Now, we have it in the form of something we can take the derivative of. A number times x to some exponent. Okay? So, what do? We bring our current exponent down, as per the required thing for the power rule. Negative 2 times negative 2 over 5 is going to be positive 4 over 5. I'll just write this, f prime of x. That's going to be positive 4 over 5, right? And now that's multiplied by x raised to the negative 2 over 5 minus 1, which is the same thing as negative 2 over 5 minus 5 over 5, which is negative 7 over 5. Now let me just go through converting this back, because this is our final answer. That's the derivative. But sometimes you might be asked, the question might say, I don't want any negative or fractional exponents, and that's like a question-specific thing. So to convert this back, well, we do it in reverse order, right? Before we did the radical first, and then we dealt with the fraction. Now we're going to deal with the fraction first, and then change it back into a radical. So first thing I'm going to do is bring this x to the denominator. So it becomes 4 over 5 times x to the positive 7 over 5. Next, I change it back to a radical. And my final answer becomes 4 over 5 times the 5th root of x to the 7th. Okay? So that's kind of the most complicated thing you're going to have to convert. However, I think using the power rule, there's very, very little change in difficulty in terms of what kind of question you have, whether you're dealing with radicals, negative exponents, fractional exponents, whatever it is, because the method is very quick, very straightforward, just a couple of steps. So just to kind of review, what we want to do, what we want to look for when using the power rule is just a number times x to some exponent, right? So 10 times x to the 4th, negative 7 times x to the 3 over 2, like whatever that is. That's the form we're looking for. Then, in order to take the derivative, we bring down the exponent and multiply it with the existing coefficient, right? That's how we get this a times n term. And then we decrease the exponent by 1. So if your original exponent was 5, your new exponent after taking the derivative is 4. If your original exponent was negative 7, your new exponent is going to be negative 8. Okay? And last things to note is, even though you might not be immediately given something in the correct form, you can convert it, right? So we've seen that with fractions and radicals, right? So anytime you see those, that's what you want to look out for. Can I convert this? And two last things, the shortcut of shortcut methods, right? That would be anytime you have a number times x, the derivative of that is just the number, right? So derivative of 8x is 8, derivative of 100x is 100, derivative of negative, 4 thirds x is just negative 4 thirds. And also the derivative of any constant is a constant. Derivative of the derivative of a constant is 0. Derivative of 5 is just 0. Derivative of 100 is just 0. Derivative of negative 4003 over 2 is just 0. So hopefully that should be a pretty, in-depth explanation of what the power rule is, different situations where you can use it, and just its utility, how useful it is. If there are any questions, throw it down in the comments, but that's pretty much it.